In the previous lessons, we learned how to calculate the dynamic response of a single degree of freedom system under various types of loadings. So we have calculated these responses analytically because the forces we have considered so far could be expressed as analytical functions. So we could find the responses analytically either directly from the differential equation or using the Duhamel integrals. So now let's see how to calculate the dynamic responses numerically. Now let's see the solution of a single degree of freedom system to an arbitrary excitation. As we have seen earlier, this is the equation of motion of a linear system under arbitrary excitation. So this is mx double dot, that is the inertia force, plus cx dot, that is the damping force, plus kx, that is the spring force, is equal to the arbitrary force. So if the system is non-linear, then the spring force term will also be non-linear. So here the force Pt is varying with time arbitrarily. This is only an example of an arbitrarily varying force. This variation could be anything. So we have learned that the response of an arbitrarily varying function can be found using Duhamel integrals. So in this case, we can represent this arbitrarily varying force as a series of impulses, and the response can be found out using the impulse response functions. So in the last week, you learned that this ht minus tau, that is the response of a single degree of freedom system to a unit impulse. So response due to this arbitrarily varying function can be found out as the sum of the responses due to multiple impulses. So if you evaluate this integral, we can get the response of the single degree of freedom system due to this force. This integral can be evaluated analytically if we can express this forcing function as an analytical expression. So in the case of a step force and a sine wave pulse, we could represent this forcing function as an analytical expression. So we could evaluate this integral analytically. But if the force is varying arbitrarily like this, for example, we cannot solve this integral analytically. And also, if the structure is non-linear, then this term will be also non-linear. So in that case also, solving this integral analytically will be impossible. So we have to solve this integral numerically. So the solution for a single degree of freedom system under an arbitrary excitation can be found out using time-stepping methods. These methods can be implemented using computer programs. Now let's see how a numerical solution is found out. So as the first step, we can represent this forcing function as a series of forces acting at different time instants. So this forcing function Pt can be represented as P0, P1, P2, etc. acting at T0, T1, T2, etc. So at time instant I, that is when time is equal to Ti, the force we know it as Pi. So at time is equal to Ti plus 1, force is equal to Pi plus 1. So at any time instant I, we can rewrite this equation of motion as mx double dot I plus cx dot I plus kxi is equal to Pi. So at each instant, we can rewrite this equation with respect to the displacement, velocity and acceleration at that instant I, and using this force at that instant I. So you can solve this equation to get xi. To find the displacement, velocity and acceleration at the I plus 1 instant, we can solve the equation of motion at t is equal to ti plus 1, that is mx double dot at I plus 1 cx dot I plus 1 plus kx I plus 1 is equal to pi plus 1. So if we solve this, you get the displacement, velocity and acceleration at t is equal to I plus 1. So each instant, each time instant, we can solve this equation of motion and find the responses at each of these instances. So we can find the displacement response at t0, t1, t2, ti, ti plus 1, etc. by solving these individual equation of motion and calculate the values of x1, x2, xi, xi plus 1, etc. And there are many methods available in the literature to do this. In this lecture, we will be exploring some of those methods. The first method is based on interpolation of excitation, that is the interpolation of the forcing function. This method is suitable for linear systems, and in this method the excitation, that is the forcing function, is interpolated over each time integral. So between ti and ti plus 1 the forcing function is interpolated. So this is the forcing function. The blue curve shows the actual forcing function, and we know the value of the force at Ti and Ti plus 1. So at Ti, the force is equal to Pi, and at Ti plus 1, the force is equal to Pi plus 1. So in between, that is between Ti and Ti plus 1, in this interval, the forcing function is interpolated as shown here. Here it is interpolated linearly. So we will use this linear variation of the force in calculating the response during this interval. So the forcing function in this interval can be expressed as Pi plus delta Pi by delta Ti tau. So tau is the time variable in this interval, and delta Pi is the difference between Pi plus 1 and Pi. So it is delta Pi is equal to Pi plus 1 minus Pi, and delta Ti is Ti plus 1 minus Ti, that is this time interval. So this is the forcing function for this interval. The equation of motion during this interval can be written as mx double dot plus cx dot plus kx is equal to this p tau, that is pi plus delta pi by delta ti tau, and this expression is valid in this time interval. So solving this equation of motion, we can find the response of this single degree of freedom system during this interval, and that response will be sum of three components. First one is the free vibration due to initial displacement and velocity at tau is equal to 0. That is, at time is equal to ti, this single degree of freedom system will have some displacement and velocity. So that will be the initial displacement and velocity for this time integral. That is the time integral between ti and ti plus 1. So because of that initial conditions, there will be a free vibration. So the first component of this response will be that free vibration, and then there will be response due to a step force equal to Pi. So the force in this interval is equal to Pi plus delta Pi by delta Ti tau. So there will be vibration due to this step force Pi. So that is this response due to step force Pi plus response due to this ramp force, that is this delta Pi by delta Ti tau. So the total response during this interval will be the sum of these three. So the total response in this interval would be, for undamped systems, it is equal to x tau, this xi cos omega nt plus x dot I, that is the velocity, divided by omega n sin omega n tau. So that is the free vibration response, and the total response will be free vibration plus vibration due to step force, and that is equal to this, and this we have derived earlier. So that would be Pi by k 1 minus cos omega n tau. Then we have vibration due to ramp force. So that would be delta Pi by k tau by delta Ti minus sin omega nt by omega n delta Ti. So this also we have derived earlier. So the total response of the single degree of freedom system in this interval is equal to this, the sum of these three vibrations. And if we differentiate this, we would get the velocity in this time interval. So the velocity would be equal to this. So if we substitute delta Ti, that is the time step value, instead of tau, we would get the displacement and velocity at I plus 1 time instant, at t I plus 1. So the displacement xi plus 1 and velocity x dot I plus 1 can be found out by substituting the value of the time step in these two expressions. So we get xi plus 1 and x dot I plus 1 as this. Just substitute the value of delta Ti instead of tau. So this depends on Pi and delta Pi. So we can substitute the value of delta Pi. Delta Pi is equal to Pi plus 1 minus Pi. So we can substitute that in these two expressions, and we can rearrange this expressions so that we would get xi plus 1 is equal to axi plus bx dot I plus cpi plus dpi plus 1. So if we rearrange this expression, we would get this expression where a, b, c and d are coefficients in terms of cos omega nt, sin omega nt, etc. So we will talk about these coefficients a little later. So if we rearrange this equation, we will get this, and this is in terms of velocity, displacement and force at xi, that is the ith time instant, and the force at I plus 1 time instant. So all the terms in the right hand side are known terms. So using that, we can find out the displacement at the I plus 1 time instant. Similarly, if we rearrange this equation, we will get this expression. And here again, this a prime, b prime, c prime and d prime are functions in terms of sin omega t and cos omega t. These formula are called recurrence formula. So if we know the value of the displacement and velocity at ith time instant, we can calculate the value of the displacement and velocity at I plus 1 time instant. So similarly, we can calculate the displacement and velocity for each of the time instants. The coefficients in the recurrence formula for an underdamped system are given by these expressions. So these can be derived, but we are not going to the derivation because of time constraints. So if we substitute the value of zeta is equal to 0, we would get the coefficients for the undamped system. So if we rearrange the terms in these two expressions, we would get the coefficients for the undamped system. So that would be equal to, if we substitute the value of zeta is equal to 0 in these expressions. So these coefficients depend upon the damping in the system and the frequency and the stiffness of the system. And it also depends upon the time step, that is delta t. So if we know these coefficients, we can calculate the responses at each time instance. And if delta t, that is the time step, is constant at each time instant, then we have to evaluate these coefficients only once. Otherwise, we need to evaluate it for different values of time steps. So in most of the cases, we will be using a constant time step. So we need to evaluate this only once. So to calculate the response of a single degree of freedom system numerically, so we will be knowing the mass, stiffness and damping of the system, and we will also know the initial conditions, that is the initial displacement and initial velocity, that is velocity and displacement at time is equal to 0. And we will also know the forcing function, that is the force series, the value of the force at different time instants t0, t1, t2, etc. So all these will be known to us, and we need to find out the responses at the i+1 time instant. So we can calculate the time step, that is delta ti, as the difference between time i+1 minus ti. So that would be the time step, and we can calculate the response, displacement and velocity response at each instant using the recurrence formula. This we have seen earlier. So if we know the initial conditions and the forcing function, we can find the response for any time instant. And this coefficients a, b, c, d and a prime, b prime, c prime and d prime can be calculated using the expressions which we have seen in the previous slide. So after finding out the value of the displacement and the velocity, we can find the value of acceleration by substituting these values in the equation of motion. So at the i+1 time instant, the equation of motion is given by this. So all other terms other than this acceleration term are known to us. So substituting all those, we can calculate the value of the acceleration. Similarly, we can find the value of the responses at other values of I. Now let's solve an example problem using this numerical method. So in this, we have an undamped system with some mass and k, and a pulse force, a half sine wave pulse force is acting on the system, and the pulse force is given as 15 sine pi t by 0.5 when time is less than 0.5 seconds, and the force is 0 if the time is more than 0.5 seconds. And the mass and the stiffness of the system are given by this. So we know the analytical solution of this pulse response as we have seen in the previous lectures. So when time is less than 0.5 seconds, that is under the force vibration, the response is given by this, that is P naught by K. P naught is the amplitude, that is 15. P naught by K, 1 by 1 minus frequency ratio square times sine omega t minus frequency ratio times sine omega n t. So this will be valid when the system is under forced vibration, and we can also find the free vibration of the system after 0.5 seconds using the displacement and velocity at this 0.5 seconds. So through this we get the displacement and velocity at this point, and substituting that here as initial conditions, we can find the free vibration response for any time more than 0.5 seconds. So now let's solve this problem using the method of interpolation of excitation. Since this is a numerical method, we will implement it through a computer program. So here we will solve it using MATLAB. Here I am just demonstrating how this numerical method is implemented using MATLAB. When you do it, you can use the computer program or platform of your choice. So here I'm just inputting the values of the stiffness and mass, and this code is written for damped systems. So for undamped system, as in our example, I can set the value of zeta as 0. So I'm choosing a time step is equal to 0.25 initially, and I want to find the response of the system for up to 3 seconds. So this is how the forcing function is written. So for each time instant, the value of the forcing function can be calculated as 15 times sine pi t by 0.5. So this is what was given in the example as the forcing function. So when the time is more than 0.5, the force is 0. So this is how the forcing function is written. Then I have chosen the initial conditions, that is the value of displacement and velocity at time is equal to 0. So I have chosen 0 initial conditions. So using the value of mass and stiffness, I can calculate omega n, and using the value of zeta, I can calculate omega d, that is the natural frequency of the damped system. So here zeta is 0, so all these two values will be 0, and this is the damping coefficient. Now we can calculate those coefficients in the recurring formula. So we had a, b, c, d, and a prime, b prime, c prime, and d prime. So we can calculate all that. So if the time step is constant, we need to calculate it only once. So after this coefficients are calculated, we can calculate the response for each value of time instant. So I can calculate it in a loop. So for each value of I can calculate the displacement, velocity, and then acceleration. So this loop will continue, and I will get the values at all the time instants till 3 seconds. To check the accuracy of the numerical method, we can compare this numerical response using the theoretical response, that is the analytical response we already know for a pulse excitation. So here I'm just calculating that theoretical response. The expression of it is given in the slide. So after calculating the theoretical response, we can plot the results for the numerical and the theoretical response. So let's run this program. So when you do this evaluation for a time step is equal to 0.25 seconds, this is how the forcing function looks like, and this is the displacement, this is the velocity, and this is the acceleration. So here the forcing function is triangular in shape, but our expression was for a half sine wave pulse. Why this is a triangular? Because the duration of the pulse was 0.5 seconds and we chose a time step is equal to 0.25 seconds. So if we choose time step as 0.25 seconds, we will get only 1 point during the pulse. So this sine wave pulse will become distorted like a triangular pulse. So this is the displacement plot. So the numerical solution is given by the blue line and the theoretical solution is given by the red line. So here, as you can see, there is some difference between the numerical solution and the theoretical solution. So the velocity and acceleration are plotted like this. So now let's find the response by reducing this time step. So let us change this to 0.1 second. So we have reduced the time step. Now let's find the response. So now the forcing function looks almost like a half sine pulse. So here, as you can see now, the error between the numerical and the theoretical response of displacement has reduced now. And again, this is the velocity and the acceleration response. Let's decrease the time step even further. So let's make it 0.05. 0.05. So now this is very close to a sine wave, and the error between the numerical and theoretical response is very less. The error has reduced considerably. Let's reduce the time step further. Let's make it 0.01 seconds. So now the forcing function becomes a perfect half sine wave and the responses are very smooth. And in the case of displacement, the numerical and the theoretical values match perfectly. So the accuracy of the numerical solution depends upon the value of the time step. As the time step increases, the accuracy decreases, or as the time step decreases, the accuracy increases. So now let's see another example. So the only change here is that the system is damped with a damping ratio of 0.05. So let's see the numerical solution of this. So we can use the same code, but we can change the value of zeta as 0.05. That is 5% damping. So let's run this. So this is the response with a time step 0.01. Here I am not comparing it with the theoretical solution, but as you can see here, since this is a damped system, the amplitude of the response of the displacement, velocity and acceleration reduces with time. So that's because this is a damped system. So if we had chosen some other time step, for example, say 0.1 seconds, the solution would not have been very smooth and the forcing function also would not be perfect sine curve. It would be slightly distorted. In the next example, we will find the response of the single degree of freedom system due to earthquake ground acceleration. So this is an example of an earthquake ground acceleration. So during an earthquake, the force acting on the system is equivalent to minus mass times the ground acceleration. So this is the forcing function, that is this acceleration times mass, and in the opposite direction. So let's solve this using the same numerical method. We can use that numerical method for any linear system. So let's use that and solve for this force. So this is the same code. So here we will change the forcing function. So instead of a sine wave pulse, we will use an earthquake acceleration. So I'm reading it from this file. So I can get the time and the acceleration in g. So if I read this value, I will get it like time versus acceleration. So I will get the data as a table. So I'll calculate the forcing function as minus mass times the acceleration. The acceleration is given in g, so I'm converting it into inch per second square. And the time step needs to be calculated according to the value of the time instance in this file. So that is calculated here. So now we can calculate the response using the same set of formulation. So let's find the response. So the time step in this forcing function is 0.02 seconds. So this is how the force is varying. So this is the forcing function. So this is equal to minus mass times the ground acceleration. So the displacement, velocity and acceleration are given by these curves. So irrespective of the nature of the forcing function, we can calculate the response numerically using this method. But this method using the interpolation of the excitation is valid only for linear systems. So it is not suitable for nonlinear systems. The next numerical method we are going to discuss is central difference method. This method is based on finite difference approximation of time derivatives of displacement. That means finite difference approximation of velocity and acceleration. So what are these finite difference approximations? So in this method, we can approximate the velocity at ith time instant can be written as the displacement at the next instant minus displacement at the previous instant divided by 2 times the time step. So this xi plus 1 is the displacement at the I plus 1th instant. So we are calculating the velocity at the ith instant. So we are taking the difference in the displacements at the next and the previous instance, and we'll divide that by 2 times the time step. So this gives us an average velocity between I minus 1 and I plus 1. As delta t tends to 0, this becomes the differential and this becomes the exact instantaneous velocity. But in this method, we will treat this approximation as the velocity at ith instant. Similarly, we can also approximate the acceleration using finite difference. So, the acceleration at the ith instant is equal to the displacement at the next instant minus 2 times the displacement at the present instant, that is ith instant, plus displacement at the previous instant, and it's divided by delta t square, that is time step square. So in this method, it is assumed that we know the displacement at the previous instant. That means this xi minus 1 is assumed to be known. So we know that the equation of motion at the time instant I is given by mx double dot at I plus cx dot I plus kxi is equal to pi. So we can substitute these finite difference expressions into this, and this equation will become mx double dot, that is this expression, plus c x dot, that is this expression, plus kx is equal to p it at instant I. We can rearrange this equation. So if you rearrange it, we have the coefficient of xi plus 1 as m divided by delta t square plus c by 2 delta t. So xi plus 1 is unknown now, and we already know xi minus 1 and xi. So every term in the right hand side is known to us. So we can find the response at I plus 1 instant. So we can represent this value as an effective stiffness. So if we can express this value as an effective stiffness, and the right hand side is force minus these terms, and we can express this right hand side as an effective force, because the unit of every term in the right hand side is that of the force. So we can express this as an effective force. So we can calculate this displacement at I plus 1 is equal to this effective force divided by this effective stiffness. After calculating the displacement at I plus 1, we can substitute this value in these two expressions and calculate the velocity and acceleration at ith time instant. So now let's see the steps for calculation of response using central difference method. So initially we will be knowing the mass, stiffness and damping of the single degree of freedom system, and we will also be knowing the initial conditions, that is the initial displacement and the initial velocity. The forcing function is also known. So we know the value of the force at each of this time instants, that is P0, P1, P2, etc. And we can calculate the time step as the difference between the consecutive time instants, that is ti plus 1 minus ti is equal to the time step delta t. So we know the initial displacement and initial velocity. So we can substitute that in the equation of motion. We also know the initial value of the force. So we can calculate the initial acceleration using the equation of motion. And after calculating the initial acceleration, we can calculate x minus 1. So in the previous slide, we have seen that the velocity or acceleration at one time instant depends upon the displacement at the previous time instance also. So we know the displacement, velocity and acceleration at time 0. So we can calculate the displacement at the previous time instant. That means the displacement prior to the application of the force. So that is x minus 1. So we can calculate that using the expression, the finite difference expression for acceleration. So using this formula, we can calculate x minus 1. And now we can calculate the effective stiffness, mass divided by time step square plus c divided by 2 delta t. So all these quantities are known. So we can calculate the effective stiffness. So after these things are calculated, we can calculate at each instant, we can calculate the effective force, because the force varies with time. So the effective force will be different at each time instant. So at each instant we can calculate this effective force. So in this all the quantities are known now. So the force at all the instants are known, and the displacement at the previous instant is also known, and we also know the displacement at the present instant. So we can calculate this effective force at the ith instant, and now we know the effective stiffness and the effective force, so we can calculate the displacement at the next instant, that is xi plus 1, using this formula. We can just divide this effective force at the ith instant divided by this effective stiffness to get the displacement at the next instant, that is I plus 1 instant. So once xi plus 1 is known, we can calculate the value of velocity and acceleration at I. So, and this can be repeated for different time instants. That is, we can repeat this for different values of I. So if I is equal to 0, we can get this expression as p cap 0. So for that we need p naught, which we already know, and x minus 1, which we have calculated here, and x naught, that is the initial displacement we already know from the beginning. So using these we can calculate x1, that is the displacement at the next instant. So after a time difference delta t. After calculating xi plus 1, we can substitute that value and calculate the values of velocity and acceleration at instance I. Now let's solve an example using central difference method. So this is the same example which we solved earlier, and we have a single degree of freedom system, and the forcing function is a half sine pulse. So let's solve this using a MATLAB code. As we did earlier, we can assign the values of the known parameters, that is stiffness, mass, damping ratio, time step, and the duration for which we need the response, etc. So here I am calculating the response for 3 seconds, and our forcing function we can define. So this forcing function is 15 sine pi t by 0.5. So 0.5 seconds is the duration of the sine pulse. So the forcing function is defined, and we can calculate the natural frequency and the damped natural frequency and the damping coefficients. We already know the initial conditions. They are equal to 0, the initial velocity and initial displacement. We can calculate the initial acceleration and also the displacement prior to the application of the force, that is x minus 1. So after calculating this, we can find the effective stiffness, that is K effect here, and we can also calculate the effective force and the displacement at the I plus 1 instant. So we can calculate these for different values of I. So we can do that in a loop. So if we do that, we will get the displacement history. So we'll get the displacement for each time instant. So here I'm calculating only the displacement now. So if we want velocity and acceleration, we can just substitute the expression of them in this loop, and we can calculate those also. So presently the time step is 0.01 seconds. So let's see how's the response. Calculate the response. So this is the displacement response for the system, and this is calculated for a time step is equal to 0.01 seconds. So this is similar to the response we have seen using the previous method. So since the time step is very less, the response which we are getting is very smooth. So let's find the response for an increased value of time step. So let's find it for 0.05 seconds. So when the time step is 0.05 seconds, the response is approximately equal to the previous response, that is with a time step of 0.01 seconds. So the amplitude is close enough and the response is slightly distorted because of the increased time step, but the values are approximately equal. Now let's increase the time step further. So let's make this 0.1 seconds. So with 0.1 seconds, the response gets distorted further. Let's see what happens if we increase the time step further. So let's change this to 0.2 seconds. So now with the time step of 0.2 seconds, the response is this. And this behavior is entirely different from what we have seen with lesser value of time step. So the actual response and the response we got for lesser value of time step was decreasing with time. So because of the damping, the response was decaying with time. But this behavior we are getting now is the opposite. Here the response is increasing with time. The amplitude increases with time. And let's see what happens if we change this to 0.25 seconds. So when we are increasing the time step further, the response we get is this for up to 3 seconds. So this amplitude is very high. So this response is kind of meaningless for the system we are solving for. So what led to this meaningless results? That is because of the larger time step. So this method, this central difference method, is stable only if the time step is small enough. That is, if the time step divided by the natural period, if that quantity is less than 1 by pi, then only this central difference method is stable. So if this time step divided by natural period value is more than 1 by pi, then we will get meaningless response. So the response values we will be getting through this method, if the time step is not small enough, will be meaningless. So whenever we are using central difference method, we need to make sure that our time step is smaller than 1 by pi times the natural period. The next numerical method is called Newmark's method. It is a family of methods. So in this method, the velocity at the time instant I plus 1 is approximated in terms of the velocity at ith time instant and the accelerations at ith and I plus 1 time instants. And this gamma is a parameter which controls the variation of acceleration between the time steps. And the displacement can be approximated using this expression. So the displacement at time instant I plus 1 can be approximated in terms of the displacement at I and the velocity at I and acceleration at I and I plus 1. Again, this depends upon another parameter, beta. Parameters alpha and beta controls the variation of acceleration between two time instants. And we know that the equation of motion at time instant I plus 1 is expressed like this. So this equation of motion can be used to find out the value of acceleration at I plus 1. So if we look at these equations, we can see that the expressions for velocity and displacement at I plus 1 depends on the value of the acceleration at I plus 1. And this acceleration at I plus 1 also depends on the value of displacement and velocity at I plus 1. So we cannot calculate the value of acceleration explicitly. So we need to solve these equations iteratively. These three equations can be solved iteratively, and the values for displacement, velocity, and acceleration at a time instant can be found out. And the appropriate values for these parameters gamma and beta are given by gamma is equal to half and beta is in between 1 by 6 and 1 by 4. So these two parameters define the variation of acceleration over a time step, that is between two time instants. And these also determine the stability and accuracy characteristics of this Newmark's method. So depending upon the values of gamma and beta, the stability and accuracy of these methods will change. For linear systems, these equations can be solved without iteration. So we can define these incremental quantities as the difference between these quantities at two consecutive time steps. So the incremental displacement, velocity, acceleration, and force are defined as this. So now we can rewrite this first equation as x dot I plus 1 minus x dot I, that is equal to delta xi. So we can rewrite this as this. Delta x dot I is equal to this quantity. So if we rearrange this, we would get this. And from the second equation, we can find xi plus 1 minus xi. If you take this to the left hand side, that would become delta xi. So we can rewrite this equation as this. And from this equation, we can find out the value of delta x double dot I, that is the incremental acceleration. So we can find out the expression for incremental acceleration from this, and we can substitute this expression in this equation, that is the equation for the incremental velocity. So here it depends upon delta x double dot I. So we can substitute this expression here and we would get the incremental velocity as this. So now we have the expressions for incremental displacement, acceleration, and velocity. We can substitute this in the incremental equation of motion. So what is the incremental equation of motion? So it is given by m delta acceleration plus c times incremental velocity plus k times incremental displacement is equal to the force increment. So we can substitute the values of delta x double dot I plus delta x dot I and delta xi into this equation, and we can rewrite this equation in terms of an effective stiffness and an effective force increment. So if you make the substitution and rearrange the terms, we can find the expression for this effective stiffness and the force increment. So they are given by this effective stiffness is given by this and the force increment is given by this. So now depending upon the value of the beta, we can have two special cases for Newmark's method. In the first case, the beta is equal to 1 by 4. The value of gamma is equal to half, and in this case, the acceleration over a time step is approximated as the average of the accelerations at the consecutive time instance. So here the acceleration over this time step is equal to the average of x double dot I and x double dot I plus 1. So in the next case, beta is equal to 1 by 6, and that is called linear acceleration method. So in this, the acceleration between two time instants, that is over a time step, is approximated as a linear variation between these two time steps. So between this ti and ti plus 1, the acceleration will vary linearly. So now let's see how the response is calculated using Newmark's method. So as we have seen earlier, we will be having the system properties, mass, stiffness and damping values. We'll also be knowing the initial conditions, and the force will also be known to us. So using these, we can do some initial calculations, and the time step is calculated as the time difference between two consecutive time instants, that is ti plus 1 minus ti. And we can do some initial calculation. So the initial velocity and displacement are known to us, so we can calculate the initial acceleration using the equation of motion. Then we can calculate the effective stiffness given by this expression. All these values are known to us, so we can calculate this value for the effective stiffness. And we can calculate these coefficients a and b given by these expressions. This will contribute to calculating the incremental force. Now, at any instant ti, we can calculate the incremental force and the incremental displacement, velocity and acceleration. So after calculating this incremental value, we can calculate the value of these quantities at the I plus 1 instant as the sum of the values at ith instant plus the incremental values. So the displacement at I plus 1 is equal to displacement at I plus delta xi. Similarly, we can calculate the velocity and the acceleration at the next instant, the I plus 1 instant. Now, let's solve our example using Newmark's method. So here, as we have done earlier, we can define our system properties, stiffness, mass, damping ratio, etc. We can choose a time step and we can calculate the response for some amount of time. So here I am choosing it as 3 seconds. So the forcing function is defined as we have done earlier. We need to calculate the natural frequency, damped natural frequency, damping coefficient, etc. We know our initial conditions, so the initial displacement and initial velocity are given. Now we can calculate the initial acceleration and the effective stiffness, that is K effective, and the coefficients A and B. So using coefficients A and B, at each time instant, we can calculate the force increment, that is, I have given the variable as del P effective. So we can also calculate the incremental displacement, velocity and acceleration, and using the incremental values, we can calculate the values at the time instant I plus 1. So this will be calculated in a loop. So once this loop is executed, we will get the displacement, velocities and acceleration values at all the time instants. So we will get the response history. We will calculate the responses for two values of beta, that is 1 by 4 and 1 by 6, that is corresponding to average acceleration and linear acceleration. So let's find this. So when the time step is very less, that is when the time step is 0.01 seconds, both the methods, the average acceleration method and the linear acceleration method, gives same values. So both the curves have overlapped here when the time step is very less. Now let's see for higher values of time steps. Let's understand how these responses using these two methods vary from each other. So when the time step is say 0.05, we would get the response as this. So here, as you can see, the responses due to both these methods differ from each other slightly. The difference increases as time increases. Let's see for another time step. So let's say for 0.1 seconds. So when the time step is 0.1 seconds, this difference is even more. So both the methods vary significantly. Here also, as the time increases, the difference becomes evident. Let's increase the time step further, say 0.25. So in this case, the responses calculated using these two methods vary significantly, and the accuracy of the average acceleration method is very less. The amplitude is very less compared to the original amplitude. Let's see this for one more time step. So if we increase the time step further, say let's make it 0.35. So now the linear acceleration method goes out of bound. So this becomes unstable. The response calculated using average acceleration method, the blue curve, is stable. But the accuracy of this response will be affected because of the large time step. But the response is stable, but the response calculated using linear acceleration approximation is unstable. So the Newmark's method is stable when delta t by Tn, that is the time step divided by the natural period, is less than 1 by pi root 2 multiplied by 1 by square root of gamma minus 2 beta. So if this value is less than this, then the method is stable, and if it is greater than this value, then the method is unstable. So it can give meaningless results. So we need to make sure that the delta t, that is the time step we are choosing, should be such a way that this quantity is less than this. So what happens when gamma is equal to half and beta is equal to 1 by 2? So when gamma is equal to half and beta is equal to 1 by 4, that corresponds to the average acceleration method. So that means this denominator is 0. So that means this method, the average acceleration method, is stable if delta t by Tn is less than infinity. That means it is stable for any value of delta t. So the average acceleration method will be always stable, but the other method, the linear acceleration method, can be unstable if this relationship is not satisfied. Now we can compare the accuracy of the three different methods by comparing the responses to the theoretical response. So in this figure, the yellow line, the continuous line, indicates the theoretical response, and the blue line shows the average acceleration method, and this red dotted line shows the linear acceleration method, and This purple line shows the central difference method. So the types of error due to this numerical formulation could be two types. The first one is the amplitude decay and the second one is the period elongation. Depending upon the time step chosen, the numerical response gets distorted compared to the theoretical response. So, the amplitude of the numerical response could be less than that of the theoretical response. So, that is referred as amplitude decay. So, that is one type of the error, and the location of the peaks will also be different from those of the theoretical response. So when the location of the peaks changes, that can lead to period elongation. So the period of the numerical response will be slightly longer than that of the theoretical response. So in an effect, this numerical response will be having some kind of a numerical damping. The effect due to the numerical approximation is same as having some type of a damping. The amplitude gets decayed and period gets elongated. And as you can see from these curves, the red curve is the closest to the theoretical response. So that is corresponding to linear acceleration method. So the linear acceleration method gives the most accurate results if the time step is within the limit. We have already seen that if the time step is higher than some value, then the linear acceleration method can get unbounded. It can become unstable. But if the time step is within the limit, then this method is the most accurate among the three methods. And so when we are doing a numerical analysis, so we need to choose a finer value of time step. So we can choose the smallest time step we can afford to choose, and once the response is calculated, we can repeat the calculation using a smaller time step and check whether both the results are converging or not. So that is one check to assure that we are using the right time step.